Here is an introduction to solar system dating to accompany Chapter 14 of the textbook Astronomy from Open Stax. The solar system is 4.6 billion years old, is something that you've probably heard before, something that I've said in earlier lectures in this class, and you might wonder, how could we possibly know that, right? 4.6 billion years is a long time ago. How can you determine the age of anything in the solar system with any kind of confidence? And in fact, you'll see 4.56 billion years old, so that's relatively precise. How do we know that? Well, in the solar system, there are lots of ways to determine ages. Some primary ways, though, are radioactive dating or radiometric dating. This is by far the most precise. Crater counting is a way to get relative ages, and we can turn that into absolute when we pair it with radioactive dating. We can compare to other planetary systems, and computer modeling gives some guess as to how things might have evolved as well. First, let's dive into radiometric dating, and so I need to do a quick introduction on radioactive decay. So most nuclei undergo radioactive decay. What's shown here in the upper right is the nuclear chart. So each box is a given isotope, and an isotope is a nucleus with some number of protons and some number of neutrons. As you go in the vertical direction, that indicates there's more protons in the nucleus. The horizontal direction indicates the number of neutrons. And the color coding here tells you which radioactive decay mode a given isotope undergoes. And it doesn't matter exactly what the colors mean here. The main thing to take away is the black are ones that don't undergo radioactive decay, and the colors, these are all the ones that do. And so most do undergo radioactive decay. And by decay, we just mean a spontaneous transmutation into a different isotope. And there's different ways that can happen. So each nucleus that can undergo radioactive decay has a given decay probability, and this is constant. This does not change at all as far as we know, at least for any standard model of physics. And for any given nucleus, the probability of it decaying is random. But when you take an ensemble of nuclei, so for instance, let's say I have several different isotopes of carbon-14, so I have a whole bunch of them collected, a thimble full of carbon-14, then we can talk about the rate of decay for that nucleus. And so this decay probability will map onto that decay rate. And this leads to the universal decay law. So it turns out when you state that the decay of a single nucleus is random and that the decay probability is constant, then mathematically this universal decay law pops out of that. And so what this says is that the amount of a given isotope that I have is equal to the initial amount times some exponential decay here. And the decay constant is this thing called lambda. So for instance, let's say I have some sample, and let's say it's 100% of some radioactive isotope. Well, it's going to undergo exponential decay, and sometime later that we call the half-life, only half of that sample is still the original radioactive isotope. And then as we go on one more half-life, only a quarter will be that original radioactive isotope. That just continues to decay there. The decay constant lambda is related to the half-life, which is a little bit easier to grasp, right? We just defined what the half-life was. The decay constant is the natural log of 2 divided by the half-life. And again, the half-life is just the time that it takes for half of your sample to undergo decay. So then let's take the most basic way to do radiometric dating. So if we knew how much of a particular isotope was in a sample, then we can look at what the abundance is now, so sometime later, and then just map back that exponential decay curve to figure out how old that sample is. Right? So let's take an example that this is done for. You've probably heard of radiocarbon dating. And so the way that this works is we're looking at the amount of carbon-14 in an organic sample. And carbon-14, the reason that the amount is, we know what the amount is in a living organism, is that carbon-14 is constantly replenished by spallation in the atmosphere. So energetic charged particles from space, either from the sun or, for instance, different distant stellar explosions, lots of different things, will send these particles into the atmosphere. They'll hit a nucleus or an atom just sitting in the atmosphere, for instance, some nitrogen. They'll bust that nucleus apart. That'll create neutrons, create lots of things, but it'll create neutrons. Neutrons can be captured by nitrogen in the atmosphere, and that nitrogen can then, when it undergoes neutron capture, can produce carbon-14. And this is happening all the time, and so there's basically a constant amount of carbon-14 in our atmosphere. And there's something called the carbon cycle, where living organisms have a constant uptake of carbon. And so in any living organism, the fraction of carbon-14 atoms to carbon-12 is constant. And as a reminder, carbon, right, that means there's 6 protons in the nucleus, and then 14 tells you the number of nucleons. Okay, so carbon-12 has 6 neutrons, 6 protons. Carbon-14 has 8 neutrons, 6 protons. So this ratio is going to be constant for any living organism. And it's approximately constant. It turns out that the cosmic ray flux can vary over time. You basically have to look at different isotopic ratios to figure out how this flux has changed. And nuclear incidents matter. So in the era of nuclear weapons testing, this ratio does change, and so you have to take that into account. But in any case, a living organism, you take it's a sample of its carbon, and the carbon-14 to carbon-12 is about constant. Once an organism dies, it's not uptaking any new carbon anymore. It's basically exited out of the carbon cycle. And so that carbon-14 is then going to decay away steadily. And so if we look one half-life after an organism has died, so a carbon-14 half-life is 5,700 years, then the carbon-14 to carbon-12 ratio is half of the original constant value. And so we can write this equation that we had on the previous slide, but instead of the absolute number, we have the ratio of carbon-14 to carbon-12. And we have some initial ratio, and that will exponentially decay, and the decay constant is natural log of 2 over the half-life. We can do a little bit of algebra and then solve for the age of any given sample based on the fraction of carbon-14 to carbon-12, the ratio of that, to the initial carbon-14 to carbon-12 ratio, which is constant for our atmosphere. And this is, for instance, how we know some historical artifacts that claim to be from a long time ago are not. So the Shroud of Turin, for instance, is claimed to be from around 0 or 33 AD, and it's actually from 1300 AD, and you can determine this from radiocarbon dating. So radiocarbon dating itself is only really useful for about 10 half-lives for any given radioactive isotope. Once you get to 10 half-lives, it becomes really difficult to measure this ratio accurately, and so you need to use a longer-lived radiochronometer, so just an isotope with a longer half-life. So that's the basic picture, but usually things are more complicated. So we don't necessarily know the initial abundance of an isotope in a sample. For instance, if you're talking about a radioactive isotope that was made in the early solar system. And you can also have chemical effects change the abundance. So for instance, let's say it's gaseous, it can escape a rock. Or you can have chemical reactions that act on different elements in a rock differently and cause certain elements to be enhanced or depleted in some way. So these are extra complications, and what we just talked about in the previous slide may be too simple. So what's done instead is to focus on isotopic ratios, and you choose a different isotope of the same element as the nucleus you're interested in as your reference. And the reference isotope has to be stable and not fed by a long-lived decay. That sounds pretty abstract, probably, but let's take an example. So for instance, rubidium-87 is a very long-lived isotope. Its half-life is around 50 billion years. Okay, so the decay constant there is rather small, but it's a very long half-life, and so you can use this to date really old stuff like the solar system or the universe itself. That rubidium-87 decays into strontium-87. And we don't necessarily know the initial ratio of the abundances here. Okay, and strontium, for instance, could evolve in your rock in a way that you don't really know, right? It could be depleted or enhanced. So we can then also take a look at strontium-86. So this is a stable isotope of the element strontium-87. It's another stable isotope, but it's not fed by a long-lived radioactive decay. So the isotope that feeds this by a beta decay only lives for 14 hours. So basically the amount of strontium-86 you have in a sample is the same as when it was made. Right? There's no radioactive decay feeding this, just however much strontium-86 sample is born with, that's how much it has. Okay. So we know, though, that also the sum of abundances along a given radioactive decay chain is constant over time. So if I start out with some amount of rubidium-87 and some amount of strontium-87, I may not know how much I had of each given one, but I know that the sum of these two is constant, because the rubidium-87 just decays into your strontium-87, and it does not decay, it just stays there. Okay, so the sum of the abundance of rubidium-87 and strontium-87 is constant, and I can take the ratio of that sum to the amount of my stable isotope that's not fed by radioactive decay, so in this case strontium-86. So this is constant. We know that our rubidium-87 will just undergo simple exponential decay, so the amount that you have at any given time is just related to the amount you initially had times an exponential decay. And you might notice that here I have the initial amount on this side of the equation and the amount at the current time on this side of the equation with the exponential, and that's because I flipped them. Right? I just did some algebra, and so you'll notice the minus sign is missing from this exponential decay here because we moved it from one side of the equation to the other. Well, then what we can also do is we can plug this into our ratio up here, right, up into this equation, and do some simple algebra. And you don't need to follow it, but basically the ratio of, in this case, my strontium-87 to strontium-86 at some given time is equal to this fraction here. So the initial amount of strontium-87 that I had, which I don't know, keep that in mind, plus the amount of rubidium-87 you have at some time, times this business here, which has the rubidium-87 decay constant up in the exponential. And again, the denominator, this is our strontium-86 amount. Now that may look complicated and not look very helpful, but if you pay close attention, you'll see this is just an equation for a line, right? This can basically be broken out into y is equal to mx plus b. So just a simple equation for a line. The slope of our line is this variable m, and this is 1 plus the, in an exponent, the decay constant of, for our example, rubidium-87, times the time since the formation of that sample that had the rubidium-87 in it. So that's the slope of the line. The y-intercept of the line is the ratio of the amount of strontium-87 to strontium-86 for our example. So what we can do is we can take lots of different samples of rocks in the solar system, so meteorites are the best thing to use, and we can measure this strontium-87 to strontium-86 ratio and the rubidium-87 to strontium-86 ratio. And we can plot that, and as we see from our equation here, this is just a line, so you get a line. So all the samples are going to fall on some line that you collect. And you know why one sample has more than the other just has to do with the formation history of that rock. But these ratios all fall along a line for the reasons that we just went through here. And we know the decay constant of our rubidium-87. We can measure that on Earth. So then the slope is just directly related to the age of the sample, t, the time since it was formed. And again, the y-intercept just tells you the ratio, initial ratio you had of that strontium-87, which is interesting in its own right. But in any case, we plot that line, and we can see that when we take a whole bunch of different meteorites, we get around 4.5 billion years for the age of these meteorites. And the meteorites are formed with the solar system, and so the solar system age then is around 4.5, 4.6 billion years. And we can take a look at lots of different isotopes, and we get a consistent picture. So for instance, we can play the same game with hafnium and lutetium isotopes, and we get some slope, and we find that the age is 4.6 billion years is what we get from this one. We can do it with lead isotopes, and we get again around 4.6 billion years. This one is an incredibly accurate one, so that's where you get the 4.56 number. And again, we have a rubidium and strontium. So there's a consistent picture, and that's how we know that the solar system is 4.6 billion years old. So why do we use meteorites and not necessarily like just regular rocks on the Earth? And that's because a meteorite doesn't have geology, right? It was formed at some small rock out in space. It's not massive enough to undergo hydrostatic equilibrium. There's no tectonic action. There's no volcanic activity. So it's just preserved in its initial state. If you were on Earth, you got to find the oldest rock you can get your hands on, and not just any old rock. And so it's not, you may not necessarily get the actual age of the Earth. So the meteorite's just the best sample to use for this, and we luckily have lots of these. Another way to get ages is to do something called crater counting. And in general, this would normally be used for a relative age unless you've benchmarked it, which we'll talk about in a moment. So the idea is that any given object in the solar system, over some stretch of time, will have a relatively constant rate of impacts on the surface of that object. So there's some amount of rocks kind of floating around in space, and sometimes those are getting kicked out of the asteroid belt, for instance, and they're going to fall onto, for instance, the moon. And that rate is, you can expect it to be relatively constant, at least over some stretch of time. And so then if you look at a given area, let's look at the moon, you can look at some patches of the moon have lots of craters, and other patches have very few craters. Right? So that tells you this area with very few craters, this must be a fresher surface than the area with lots of craters. Right? There's not some invisible force field blocking rocks from hitting here. It's just rocks didn't hit in this patch yet, or at least many fewer relative to this patch over here. So this indicates there's been some activity, and for instance, on the moon, you can tell when there's been volcanic activity in the past. You have these things called maria. Now, one complication with crater counting is that, as you might be suspicious of, this rate of bombardment of rocks on the surface of your object doesn't have to be constant. And when you use radiometric dating to benchmark it, you find, in fact, it's not constant. And so early in the solar system, there were lots of rocks kind of bouncing around from early failed planet formation, planets kind of shuffling around because of complicated gravitational interactions. There was a lot of stuff going on. And so there was a lot higher impact rate a long time ago. Then in more recent history, that impact rate has been relatively constant. And so you can use crater counting sort of for absolute dates with dating with decently high accuracy for the kind of sort of later history of the solar system. And in the early history of the solar system, you do have to benchmark carefully with radiometric dating. One issue still, even when you've done this correction with crater counting, is you can get these things called secondary craters. So you can imagine if a really big rock comes in and hits an object like the moon, for instance, let's take this crater, it's huge, right? That's a very large crater. That's going to bust apart the surface of the moon and cause rocks to fly out and cause secondary craters all around here, right? So you need to really carefully look at your craters and try to figure out if they were primary or secondary. And you don't want to count the secondary because that would be double counting, right? So that's a little bit tricky. Another tricky issue is if you have an object that has some kind of weather on it, then the craters can erode. And so, for instance, if you take a look at the number of craters of a given size per a certain amount of area, and you look at that versus time, you can see in recent history, the past 100 million years or so, you have a relatively constant rate, and then it appears to fall off. And so you see this consistently for different places in the world. And this isn't necessarily really because of a change in the bombardment on the Earth. This is really more because of craters erode, right? And so crater is just a divot with a hill around it, and erosion's going to basically wither that thing away, and so you're going to have fewer of these over time. So that's another complication that you have to take into account with crater counting. One more thing we can do is we can compare to other stellar systems, and this is really valuable for the early history of the solar system. So this is one way we can figure out what happened early on. So it's not really dating necessarily, but it's kind of one way we can assign an age to when certain things happened in the solar system, and we already talked about this in the Introduction to Planet Formation lecture. And then just rounding things out, one other way you can look at how the solar system has evolved over time and assign ages to certain events is with stellar models, or not stellar, sorry, stellar system models, so models of the solar system. And so, for instance, what's shown on the left here is the so-called Nice model, and you just saw that, boom, that orbits of the planets change abruptly, and that belt of objects that was initially there be ejected from the solar system. And this is what one model of the solar system predicts, for instance. And so you can create these models and then compare them, their predictions, to what you actually see in the solar system. And if it matches a lot of the predictions, then you can say, okay, this model probably is a decent picture of what actually happened. It's really hard to prove that this model is the correct model because there's lots of knobs to turn, basically. Another serious complication is that the solar system is a so-called chaotic system. And I mean this in the mathematical sense. And the simplest example you can give of chaos is if I take a marble and I put it on the top of a round bowl, for instance. Let's say I have a bowl that has a perfectly round bottom. I flip that bowl over and I put a marble on the top. And I let go of the marble, it's going to roll in some direction off the side of the bowl. And if for just a very slightly different set of initial conditions, let's say I set the marble a little bit to the left, a little bit to the right, like just a teeny tiny amount, the marble is going to follow a totally different path. And that is a basic example of chaos. And the solar system is chaotic. And so, for instance, you can model the solar system over time, and very small changes in the initial conditions will result in very different overall results. So what's shown here is the eccentricity of Mercury. Remember, this is like how elliptical an orbit is over time. And the difference between all these colored lines of this particular model of the solar system is that the initial position of Mercury has been moved by a tiny amount. And when I say tiny, in this case, we're talking about a millimeter or fractions of a millimeter. So for that, which is ridiculous, right? That's a very small distance for something on a planetary scale. So I move it a millimeter, and then within 100 million years or so, you have a very different eccentricity that you predict for Mercury. And so this chaotic nature means it's actually pretty hard to directly predict what would happen in the solar system, or to even model backwards and say how the solar system has exactly evolved over time. That's probably not necessarily a knowable thing in very fine detail. So what you do as a kind of solution is you do tons of model calculations, changing these initial conditions, and you can get a probabilistic sense of what happened. And so, for instance, you see that you have many more curves at this sort of lower eccentricity as opposed to the higher one, and this gives you an idea of how, for instance, the eccentricity of Mercury probably evolved over time. It's much more probable that it would have followed, this path here, where you have lots more models, but not necessarily, right? It's only probabilistic. There's nothing forbidding following the solar system having followed a low probability evolution, for instance, in the case of this eccentricity. So in the end, we'll never know exactly how the solar system came to be the way that it is. We can just get a decent semi-quantitative picture. And that is it for this introduction to solar system dating for Astronomy 1000.